Hi, good morning, everyone. I hope you all had a wonderful spring break. So we're going to start reviewing for our IA. That'll be on Friday morning. So this is going to be some examples of FRQs that are totally fair game for your IA, even the AP exam. So please make sure you take good notes through this because they're for this week and every week continuing, you are going to have to submit images of your notes that you take from these examples. So please make sure you do so, or you take notes as you're watching these videos. All right, so let's get started with number 1 here. The Department of Agriculture at a university was interested in determining whether a preservative was effective in reducing discoloration in frozen strawberries. A sample of 50 ripe strawberries was prepared for freezing. Then the sample was randomly divided into 2 groups of 25 strawberries each. Each strawberry was placed into a small plastic bag. 25 bags in the control group were sealed. The preservative was added to the 50 bags containing strawberries in the treatment groups, and those bags were sealed. All bags were stored at 0 degrees Celsius for a period of 6 months. At the end of this time, after the strawberries were thawed, a technician rated each strawberry's discoloration from 1 to 10, with a low score indicating little discoloration. The dot plots below show the distribution of discoloration rating for the control and treatment groups. Okay, so the first part here, we want to compare the distributions for the control and treatment groups. So we know that when we are comparing distributions, anytime we see this sort of describe distribution or compare, we should automatically think of our SOCS, so shape, outlier, center, spread. So looking at these, we need to compare them. So I'm going to just off to the side put a note of SOCS for each of my distributions. So let's do these in different colors here. So the black one will be my treatment group, the red one will be my control group. So looking at the shape for the first treatment, I see that we are pretty symmetric here. For outliers, I don't really see any, so that's fine. The center, I want to use probably the median here. So if I go ahead and just quickly find the median, since there are 25 strawberries in each group, I'm just going to count from the left 12, and that'll give me my halfway point. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so this is going to be where my median's going to lie, so that's 5. So my median is equal to 5 here. And then my spread, so we can do this in a number of ways. We can do the IQR or the range. Let's just go ahead and do the range here. So 1 and 10 is our max, so the range is equal to 9. Okay, for our second distribution, we are also pretty symmetric here. We don't really have any outliers. Our center, let's go ahead and find the median. So again, there should be, let's find the midpoint of 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the 13th, which will be our middle, is actually going to be this calibration is not working super well. So this dot right here. So that is the 13th dot. So that is going to be our median. So our median here is actually equal to 7. And then our range is also going to be 9. So I've quickly just gone through, and now I'm going to actually compare my distributions. So for part A here, to compare them, the control group and treatment group have relatively the same shape. both with no outliers. The median of the, which one? The control group. Let's just say 7, well, the median of the control group with a rating of 7 is greater than the median of the treatment group with a rating of 6. So again, we are comparing these, so this greater here is really key in the comparison aspect. And then we can say the two have the same range of 9. Okay, so we've listed every aspect here. So again, make sure we are comparing. So what is similar between them, what is different, and how is it different? So the only thing that was really different here was the median, and we specifically use the word greater than. Okay, so part B, we're going to describe the shape of the distribution if one were to combine the two dot plots into one dot plot. Okay, so this is a little strange here, so I don't think we've ever really done this. If we have, we've probably only done it like one time. So if we want to combine these two graphs together, so essentially we're adding all of these dots into one graph. And then we need to talk about the shape of that graph if we were to put all of the dots on one graph. So we can see that the median for this here is, hold on, I may have made a mistake here. Yes, I apologize. Now that I'm looking at this graph a little closer, I said 5, but I wrote 6 for the median of the treatment group. So let me fix this here. I apologize, so please correct that in your notes. Hopefully you caught that in real time. Okay, so we see that the median for the treatment group is less than. We already described that. So if I were to add all of these dots on top of each other, we would see that sort of the highest points here would most likely be around the 6 mark. So we would have a lot of dots there, and we can see that we sort of have a lot of dots on the right-hand side of the control group. So this is sort of the majority of our dots here. We're pretty relatively symmetric. You could probably make an argument for skewed left here. But since we're both relatively symmetric, I'm going to combine these, and we can see that we are also going to be relatively symmetric. And so now I want to, since they're just asking for the shape, I'm going to describe both the symmetry and both the modal. So for the shape, here, since they're saying shape, I want to do both the symmetry and the modal, because they're only asking for the shape, so I'm not going to have to go through the center and the spread and all of that. So we can, this is the easiest part really, is to just say the symmetry and the modal. So if I put this graph on top of each other and I add all these dots together, since both of them are relatively symmetric, we're going to see that we're still going to be relatively symmetric in our new graph. And then we can see that the highest point here will be 6, between 5 and 7, and it's going to be like the highest points in our graph. So therefore, we're still going to be unimodal, just as both of these graphs are. So if I combine these two graphs, and now that won't always be the case. So don't think that just because both of these graphs are symmetric, both of them are unimodal, when you put them together, the product is still going to be symmetric and unimodal. That doesn't always happen. So you really have to use your visualization skills to think about what's going to happen. So here, since we can just say the shape of the combined graphs will be symmetric and unimodal. Okay, and so now part C. The university collected data from every frozen strawberry in the US, and the shape of the distribution of the population was the same as the shape of the combined dot plots in part B. Okay, so they're saying that they took the population and they said that it's the same as what we described above, okay? And it has a mean of 6 and a standard deviation of 2.71. So suppose the university took another sample of 50 strawberries, describe the sampling distribution. Okay, so they're asking us to describe this sampling distribution. So when we describe a sampling distribution, we're still going to follow the SOX model. However, we have to be more specific. So when we are doing sampling distributions, we have our SOX. However, this time when we describe the shape, we need to talk about the normality of it. Is it going to be normal or not? We don't really need to say anything about outliers here because sampling distributions don't tend to have outliers. But if you feel so inclined, you can say no outliers. That's fine. The center, I'm going to talk about the mean. And the spread is the standard deviation. So when I see sampling distribution, these are the things that I need to talk about. Normality, the mean of the sample, because we're describing sampling distribution. So mean of the sample and standard deviation of the sample. Okay, so when I'm writing this up, I need to think about how, well, first, am I looking at a sample distribution of means or proportions? So since we're looking at ratings here, this isn't really a percentage or anything like that. So this is going to be a sample mean. So for a sample mean, I'm just going to use the mean that they gave me. So the mean of the sample is equal to the mean of the population. So we can say that the sample mean is equal to 6. And then the standard deviation, we know that S is equal to sigma over the square root of n. So here the population standard deviation is 2.71. So that's going to be equal to 2.71 divided by the square root of our sample size. So let me go back. And we took a sample of 50 strawberries. So that is going to be our sample standard deviation. And so now we've hit the mean, we've hit the standard deviation. The only thing that we have left to talk about is the normality. So since we said that this is a sample mean, I need to think about how do I determine the sample mean or the normality in a sample mean. So we know that for a sample mean, that is n is greater than or equal to 30, means that we are normal. If it's less than 30, then we just follow the parent population shape. So in this case here, we would be normal since our n is 50. So we can say the shape, well, yeah, that's fine. The shape of the sampling distribution of sample means is approximately normal. So this is a key piece here. It's not necessarily going to be normal exactly. It's going to be approximately normal, just because we can't say normal 100%. It's going to be approximately normal. since, and this is a make it or break it thing. If you just say normal, you are not going to get full credit on your IA. You're not going to get full credit on the AP exam. We say approximately normal here. And a lot of you have been doing that, but I just really want to reiterate that this is approximately normal since n is equal to 50, which is greater than or equal to 30. The mean of the sample is a rating of 6, and the standard deviation of the sample is, and let's go ahead and calculate that. So 2.71 divided by the square root of 50, and that is 0.38. There we go. And that's all we have to do. Okay, so that is all of number 1. So again, please make sure you're taking note of this and you are submitting your notes on Google Classroom. Now we're going to look at number 2. So a large company has 2 shifts, a day shift and a night shift. Parts produced by the 2 shifts must meet the same specifications. The manager of the company believes that there is a difference in the proportions, so that's important here, of parts produced within specifications by 2 shifts. To investigate this belief, a random sample of parts that were produced on each shift were selected. For the day shift, 188 of its 200 selected parts met specifications. For the night shift, let me highlight this here. For the night shift, 180 were selected parts met specifications. Use a 96% confidence interval to estimate the difference in proportion of parts produced within the specified specifications of 2 shifts. Okay. So let's go ahead and just extract what we're given. So we're looking at a difference of proportions. So I know that I'm going to need 2 sample proportions here. So I'm going to have p hat of the day shift. So we're going to put p hat sub d is equal to 188 over 200. The p hat of the second shift, the night shift, is going to be equal to, well, let's just actually calculate this out. So 0.98. The day shift, the night shift is 180 over 200. So that is 0.90. I apologize. This is 0.94, not 0.98. Okay, and then I need the 2 sample sizes. So again, I should use the total sample size here, not just the parts that met specifications. So the n sub d here is going to be 200, not 188. N sub n is going to be 200 as well, not 180. So make sure that we are clear in that. Okay, so my first step when I'm doing a confidence interval, I need to check my conditions. So this is important. When we're doing a confidence interval, it's just like when we're doing a significance test. We have to test the conditions unless they say that the conditions have already been met. So we need to meet the normal condition here. So our normal, independent, and random, or if you do it the reverse way, that's fine. So the random condition that we have here, let's see, they said they took random samples of parts, so that was specified right here. So we've met the random condition. I know a lot of you are used to writing out NER or RIN and you just check it off. But let's just be more careful when, instead of just checking them off, just say random samples were taken. Just because this is an FRQ and you have to be as specific as possible. So let's just be as specific as possible. So for our independence here, we need to have our sample is over the total population. So we can say that since the sample sizes are both 200, we have assume independence here basically because we know that they're making a ton of product. So independence is assumed since 200 over infinity is less than 10%. And then lastly, the normal condition here. So this is a sample proportion. So we need to do n times p. So let's actually just give ourselves a little space and we'll do the normal condition down to here. So n times p, and this is our first p, so p sub d. That's going to be 200 times 0.94. So that's going to give us 188. And then n times 1 minus our p here is going to be 200 times 1 minus 0.94. So that's going to be 12. And both of these are greater than or equal to 10. So we've met the normal condition for the first sample here, but we need to meet it for both. So n times p sub n for the night shift is equal to 200 times 0.90, so that's equal to 180, and n times p, 1 minus p, 200 times 1 minus 0.90, that is going to be equal to 20, which are both greater than or equal to 10. So since the successes and failures in both samples are greater than 10, we can assume normality. Great. All right, so we've checked our conditions. We're good to go with those. So let's go ahead and conduct the confidence interval here. So this is a 96% confidence interval. So my C here is 0.96. So a lot of you probably can already, you have this memorized. You know that your Z is going to be equal to 1.96 here. No. Wait. 90, that would be for 95, excuse me. If this were 95%, we would use 1.96. However, I mean, it's going to be pretty close to that, but we want to be as specific as possible. So let's go ahead and just find our critical value, based on our confidence level. So in order to do that, we need to do 1 minus 0.96 divided by 2, and that's going to give us 0.02. So now I want to look on my Z table and find this percentage, because this is a percent, so I need to look in the middle. So if I go to my Z table and I look in the middle and I'm looking for 0.02, the closest that I can get to that, we can see here is going to be between these two values here. So between 2.05 and 2.06. So we're going to just go ahead and round down. So we're going to use 2.06 here as our critical value. So again, how I did that, I took 1 minus the confidence level, divided that by 2 to give me the one tail area. And then since this is a percentage, this was 96%, we looked at in the middle of the table. So that's going to tell us that Z is equal to 2.06. So my formula here is going to be P hat of D minus p hat of n plus or minus my critical value here times the square roots of my pd times 1 minus pd over n sub d plus p n times 1 minus p hat n over n sub n. So that's my confidence interval formula. And so now let's just go ahead and plug in what we know. So this was 0.94 minus 0.9 plus or minus 2.06 times 0.94, 1 minus 0.94 over 200 plus 0.9, 1 minus 0.9 over 200. And so if I go ahead and crunch that out, I'm going to get 0.04 plus or minus 2.06 times 0.027. And then that final interval will be negative 0.016, comma 0.096. So that is my final solution for parts for the confidence interval. Now, looking at the question, so we used a 96% confidence interval to estimate the difference between the two shifts. So now, based on this confidence interval, do you think that the difference of the proportion of parts produced within specifications by the two shifts is significantly different from 0? So we need to justify our answer here. So, looking at this interval, it's a great take this opportunity to really understand what this interval is telling us, and we're going to actually write out the interpretation. I know I took my time in reading part A just to make sure, did they ask us for the interpretation? But this is like when we're doing a significance test and we get our conclusion that we want to reject the null hypothesis. And then we go on to put that in the context of the problem and say, whatever we're rejecting. So using this interval, let's go ahead and just interpret what this means, just so that we get a good grasp on what exactly the confidence interval is telling us, and then that's going to help us with part B. So we can be 96% confident that the difference in proportions between the day shift and the night shift is between negative 0.016 and 0.096. Okay, so this confidence interval here is telling us that we should expect for all of the specifications differences to be between these two values. So part B is saying, is it plausible for a 0 difference for significantly different from 0? So looking at this here, 0 lies within this interval. So we can't say for sure that it's going to be different from 0 because 0 is within this interval. So we don't have evidence to say that there is a significant difference between these two shifts. So again, because 0 does not lie within the interval, we're going to say no, there is not a significant difference. So since 0 does lie, within the 96% confidence interval. We cannot determine that there is no significance we cannot I'm putting too many negatives in here and I think I'm saying the wrong thing. Since 0 does not lie within the 96% confidence interval, we cannot determine that there is significance. Excuse me. So we cannot determine that there is a significant difference between the two shifts at the alpha equals 0.04 level. So I got this 0.04 because the confidence level was 0.96 and the alpha is the complement of the confidence level, so we can just subtract that from 1. So again, how I determined this, because in a proportion test of difference, we normally would say for the null hypothesis that P1 is equal to P2. In other words, P1 minus P2 is equal to 0. And our alternate is that there is a difference here. They are not equal to each other. In other words, P1 minus P2 does not equal 0. So because 0, it could be that they are equal to 0, we essentially are failing to reject the null hypothesis here, so we cannot determine significance. If 0 did not lie within the interval, and then we would say the null hypothesis is true because it says that it's not equal to 0. So that's the rationale for this. And so our last part here, the company wants to determine if one worker from the day shift produces the same proportion of parts as one worker from the night shift. Should the company use the confidence interval from part A to determine this? Okay, so what they're essentially doing here is they're picking one person from the day shift and one person from the night shift, and they say, okay, using this confidence interval, are we allowed to make assumptions about this sample? So, this is part B. Part C. So this really goes into thinking about what exactly is a confidence interval telling us. So a confidence interval is really telling us the proportions between the two shifts, but we're estimating the population values. So these numbers that we're using here, we're trying to estimate the population. We're not trying to estimate anything about the sample because we took the sample. We know what the sample could be. But we're trying to estimate something about the population. So thinking on your own really quickly, does it make sense to make an assumption about another sample, a different sample, based on an interval that is estimating a population? So can I use an estimation from the population to estimate a sample? Hopefully your answer is no, because that wouldn't make any sense. That'd be like saying, oh, well, I know something about this orange, so that must mean the same thing for this apple. No, it's completely different, right? If I bite into an apple, I can eat the skin, but I'm not going to do the same thing with an orange. I'm not going to just bite right into it. So, in other words here, I'm not going to use the confidence interval. So it's saying, should the company use the interval from part A? No. The company should not use the confidence interval from part A to make estimations about individual values, since confidence intervals estimate population values. I could also have inserted, instead of individual, I could have said sample as well, but regardless, we're saying the same thing. No, we shouldn't, because confidence intervals estimate populations, where here we are trying to estimate another sample and we can't mix the two. So that is not a good representation here. All right, so that is the last of this example here. Please make sure you take ample notes and submit those on Google Classroom. And then we will join, please join the Zoom call so that we can do an example problem like this together. All right, have a great rest of your day, everyone.